we've met. I don't think that Everyone, here we are. So, a nice problem from 2021. So I'm just opening something here. I haven't gotten any questions from you. I haven't gotten any emails. So again, I'm assuming everything's okay. Please let me know if there's anything you need extra help with. I'm here for you. So consider the function root x. Calculate the second degree Taylor polynomial centered at 4. So centered at 4, second degree Taylor polynomial. T2 of x is equal to f of 4 plus f prime of 4 times x minus 4 plus f double prime at 4 over 2 factorial x minus 4 squared. Any doubts there? So what do we need to find this? We need f of 4, we need f prime of 4, and we need f double prime of 4. They usually give us a nice table on tests to do this. So we can create the table ourselves. So this is the n. So this is f of x, n is equal to 0, f prime of x, f double prime of x, and then f triple prime of x. We need it for the error term. We don't need it for the Taylor polynomial. We need it for the error term. So I don't know why those are there. F of x is equal to root x. F prime is 1/2 x to the minus 1/2. This is minus 1/4 x to the minus 3/2. And this is 3 over 8 x to the minus 5/2. Great. Add x equals to 4. This is 2. This is 1 over 4. This is minus 1 over 32. And this one we don't need it because it's just going to be in an interval. So t of 4 is equal to t2 of x is equal to 2 plus 1 over 4 times x minus 4 minus 1 over 32 divided by 2, so 1 over 64 x minus 4 squared. Any issues there? Right, so I took this, I replaced it here. I took this and I replaced it here. And I took this and I replaced it here. Great. Part B. It can be shown that the Taylor series is an alternating series for x bigger than or equal to 4. So we're saying they're telling us that it's an alternating series. Here you are to calculate and compare 3 error estimates that arise from using the Taylor polynomial to approximate root 0.45. So BI, they're asking us to find the actual error, the absolute value of the actual error. So find us what's T2 of 4.5 minus root of 4.5. So T2 of 4.5, you're plugging 4.5 into T2. So this is 2 plus 1 over 4 times 4.5 minus 4 minus 1 over 64, 4.5 minus 4 squared. You're literally calculating this. So what is this, and what is the square root of 4.5? Whatever, that's just a value that we're going to use on the calculator. So the absolute value of T2 4.5 minus the square root of 4.5. I'm literally entering these on my calculator. So 2 plus 0.25 times 0.5 minus 1 over 64 times 0.5 squared minus the square root of 4.5. And this is a negative number, so I'm gonna make it positive because it's an absolute value, 0.000222659. So we can say 22, whatever, something. I say, hold on. Keep 6 decimal places. So 1, 2, 3, 4, 5, 6. So 227. Great. Number 2. Use the alternating series estimate error. Okay, so what did we say is the alternating series estimation error? So if you stop at n equals to 2, the error is less than or equal to B3. So the term for n is equal to 3 in absolute value. What would have been the term if you were to go to n is equal to 3? So it turns out we needed this after all. So what's 4? This would be 2 to the minus 5 is 132. 8 times 32 is 256. So this is 3 over 256. Right? So the first term that is left out. So if I were to continue here, right? The first term that is left out, if I were to continue, so T2 at 4.5 is this. But if I were to continue, the first term that I would leave out is 256 divided by 3. No. So this would be 3 over 256 divided by 3 factorial times 0.5 to the power 3. Do we agree on this? Like, this is the first term left out. So basically that without the minus, that is B3. And we know for the alternating series estimation error that if you stop at N2, the error is less than B3. So what's 3 divided by 256 divided by 6 times 0.5 to the power 3? That is, so the error, if we use the alternating series, is less than or equal to 0.000244. You really are not saying anything. Is this okay? Okay, I'll ask the question differently. Is this not okay? Cool, thank you, Harry. So now if we use the Taylor series error bound, so we said that if we stop at T2, the error is E2 of X, right? If we stop at N is equal to 2, right? If we stop at N is equal to 2, E2 of X is the maximum value of F to the order 3. So let's use F triple prime of X divided by 3 factorial D to the power 3. Okay, I want you to tell me what D is in this case. Come on, tell me what D is in this case. Make me happy that you know what D is. So we did the Taylor polynomial centered at 4, right? The Taylor polynomial is centered at 4, and we are using it to approximate T2 of 4.5. So what's D? The center is 4, and we're using the Taylor polynomial to approximate t of 4.5. So what's D? D is how far we are from the center. Thank you, Cecilia, for answering. D is 0.5. Because our Taylor polynomial is centered at 4. We're using it to approximate t of 4.5. So the distance from the center is 0.5. Great. Now this is f3 f cubed of x. Please be careful. This is the maximum value that 3 over 8 x to the 5 over 2 can take on the interval. Now it's going to be on the interval minus 3.5. Actually, y minus 3.5 to 4.5, because this is the interval we live in now. So if you move 0.5 that way, that means to get your interval, you move 0.5 that way, and you're at 3.5. So the interval you're working with is always, remember, a minus d, a plus d. So what's the maximum value that this thing can take on this interval? Now, because x is at the bottom, so the smaller the x, the larger the value, right? You're dividing by x. So the smaller the x, the larger the value. So the maximum value that this can take is 3 over 8, 3.5 to the 5 over 2. So if you have your choices of values from 3.5 to 4.5, how do you get the biggest value of this? You get the biggest value of this by choosing the smallest value of x to get the bigger fraction. Therefore, E2 at x, the error bound at 4.5, right? That would be, this is 3 over 8 times 3.5 to the 5 over 2 divided by 3 factorial times 0.5 to the 3. Which is, if you calculate it carefully, 0.000341. And you got 3 types of errors. Okay, let's do another question. So let's go to a final. Also, this we did. Let's see what they asked them in 2020. Oh, 2020 was that strange one. I'll get to it in a second. Let's see what they asked in 2022. Here we go. Approximate this by a Taylor. Use the above to calculate. This gives us, okay, so here we go. So I'm gonna copy the question. It would have been easier if I had the questions without the answers, but whatever. We'll live. So this is from 2022. So this is A. B, no, 2022. B is, how accurate is this using an alternating series? Come on. And then, wasn't there, how accurate is this using Taylor's inequality? Right, so basically the same type of scenario. So let's see. Let's work it out. So what is the Taylor degree 2 polynomial? So we're gonna need f of x. We're gonna need f prime of x. We're gonna need f double prime of x, and we're gonna need f triple prime of x. So this is 1 plus x to the minus 2, minus 2, 1 plus x to the minus 3, 6, 1 plus x to the minus 4, and minus 24, 1 plus x to the minus 5. So at x equals to 0, we're going to get 1, minus 2, 6, and minus 24. So for part A, T2 of x is equal to f of 0, let me write it down, f of 0 plus f prime at 0 times x plus f double prime at 0 over 2 factorial x squared. So this is f of 0, 1 minus 2x plus 6 over 2, that's 3x squared. Okay, so what is how accurate is this approximation on the interval 0 to a half if we're using alternating series? Now, this is the first time we use alternating series with an interval, right? So you know that the center of convergence is 0 because we're told it's about x equals to 0. So we're at 1/2. We're technically at d equals to 1/2. You know what that this is d for the Taylor one, but how are we going to use this for the alternating series? Right. The first term that you leave out. So if you had T2 and you wanted to leave out a term, that would be minus 24 over 6, so 4x cubed. So this is the first term left out. Right? So the error is going to be less than or equal to this, right? But then we're saying on the interval 0, 1/2. So to get the error, you want to get the maximum error. Do you understand what I'm saying? Like when we say error, we mean maximum error. So the error is going to be less than or equal to 4x cubed, but then on the interval 0, 1/2. Do you understand what I'm saying? The error is less than the first term you leave out, of course, without minuses, on this interval. So what do you use? Do you use 0 or do you use a half? You obviously use whatever value x that makes this the biggest, right? Because you want to get the maximum error. You don't want to get like this. You want to get what's the worst possible scenario. Therefore, the error in this case will be less than or equal to 4 times 1/2 cubed, which is 1/2. So the error would be less than the maximum error. Of course, we're talking about maximum error. The maximum error would be a half. Great. How would you use Taylor's inequality? So how would you use E2 of x? And they're saying on the interval minus a half 0. I'm not sure if they were trying to trick people here, or they're trying to be cute, or they're trying to be like throw students off. So on 0 to minus half, again, the center of convergence is 0. You're saying I'm doing it on the interval 0 minus a half, so I'm going minus a half away from 0 maximum. So that's my d. Right? That's my d. So technically the interval is from minus a half to a half. So technically the interval, I don't know why this came up like this. So technically the interval that we're working on is a minus d and a plus d. Right, remember that this Taylor polynomial error is an error on a minus d and a plus d. So you choose whatever value maximizes f triple prime of x on this interval divided by 3 factorial times d to the power 3. Now, that doesn't change the D is 0.5. So F triple prime is minus 24, 1 plus x to the minus 5, all divided by 3 factorial, which is 6, and then D is 1/2 to the power 3. So ladies and gentlemen, what is the largest value? Again, forget about the minus. We don't care about the minus. We have 24 over 1 plus x to the minus 5, and we're looking on this interval. So what is the biggest value that we can achieve? Since we are, sorry, divided by x to the 5. Since we are dividing by 1 plus x to the 5, we want this to be as small as possible. So we get the maximum when x is equal to minus 1. So this would be 24. This would be 1/2 to minus 5, all divided by 6 times 1/2 to the 3. So I'm taking x equals to minus 1/2 and I'm plugging it here to get the maximum value. And if we do this, this is 24 over 6, that's 4, and this is 1/2 to the minus 2, so that would be 16. So that's a huge error, right? The alternating series error was 1/2. Look how nice that error was. Look at how bad the Taylor polynomial error is. The error is 16 if we use Taylor polynomial. Alternating series error is in general better than Taylor error. It gives us better results. Ready for another question? I say we are. Let's look at that 2020 question that I said I would keep it to a bit later. So let's do part A and then we'll copy part B. So this will be a good practice for both kinds of errors. So this is from 2020. F of x is equal to e to the x plus 10 cos x. So find a of x and c of x, the 8th degree Taylor polynomial for e of x and 10 cos x respectively, centered at x equals to 0. The Taylor polynomial for f of x will be the sum of this work. So you can look this up from work or from memory. We know that e to the x is equal to the summation from n equals 0 to infinity of x to the n over n factorial. And we know that cosine x is equal to the summation from n equals 0 to infinity of minus 1 to the n x to the 2n over 2n factorial. We should be a little bit careful with these finals, because some of these finals were online. So they were open book. So I don't know if 2020 was or wasn't. But always be careful. Every final comes from a semester, and there's things in the semester that happen that we may know or we may not know about. So a of x, that's the Taylor polynomial of degree 8 for e to the x. So that's a lot of writing there. So 1 plus x plus x2 over 2 plus x3 over 3 factorial plus x4 over 4 factorial, I'm really not writing all of them, plus x8 over 8 factorial. C of x, so that's the Taylor polynomial here. So when x is equal to 0, we get 1. X is equal to 1, we get x2 over 2. Then we get x4 over, and n is equal to 2, so that's 4 factorial. Minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial. And this is times 10, sorry, because it's 10 cos x. So T8, the Taylor polynomial of degree 8 of f of x, that's the Taylor polynomial of e to the x plus the Taylor polynomial of 10 cos x. So that wasn't anything particularly difficult or special. So let's see. Use Taylor's inequality. See, they even reference Taylor inequality in the workbook. So that definitely was an online exam. So let's use Taylor's inequality. So, okay, so what is E8 of x? This is the maximum value that f to the order 9 can take on x, all divided by 9 factorial times d to the 9. We're using an approximation at f of 1. So the center of convergence is 0, and we're using the approximation at 1. So what's d? D is 1. So that's very nice, because then that's just gone. Now, the question is, what's f to the order 9 at x? Well, the derivative of e to the x is just going to stay e to the x, e to the x, e to the x. So what happens to cosine? You're going to start with f prime. So f is equal to 10 cos. F prime is minus 10 sine. F double prime is minus 10 cosine. F triple prime is 10 sine. And notice when you go F quadruple prime, you go back to 10 cos. So when you get to F8, you're going to get to 10 cos. So F9 is the same thing as here. So f to the order 9 is minus 10 sine x. So that would be e to the x minus 10 sine x. And we're looking on the interval minus 1 to 1, right? Don't forget that if you move 1 to the right, you move 1 to the left, and you end up on the interval minus 1 to 1. Okay, so what is the largest value that this can be? So we're taking the maximum of this. So what we want is the maximum value that e to the x minus 10 sine x can take on the interval minus 1 to 1. Now, this is difficult to see. Because like there's no easy way of doing this. So I suppose that year they were allowed to graph it on Wolfram or something. Like it's difficult to do this very quickly unless you want to do like a long analysis of max and min. So if we go to, sorry, I thought I had Wolfram. So Desmos. Again, on your exam, it won't be this, because on your exam is not online. So really, it just can't be this. So e to the x minus 10 sine x. And then let's make this from minus 1 less than or equal to x less than or equal to 1. Again, this cannot be your exam. Let me say that again, because like you don't know how to graph this. So this is very, very difficult. So you see the maximum happens when x is minus 1. So the maximum happens when x is equal to minus 1. So the maximum happens at x is equal to minus 1. This is from an online graph. Again, this was an online test, so one expects an online graph. And everything else that I've shown you, it was very, very easy to find the maximum value. So E8 of x, E8 of 1, because if we're using x is equal to 1, that would be e to the minus 1 minus 10 sine minus 1, all divided by 9 factorial times 1 to the power 9. So if you do this, this will be 0.00002402. So if this is the maximum error, very, very important, that means your f of 1 is going to be between the Taylor polynomial at 1 plus 0.00002402 and between T8 of 1 minus 0.000242. So here we don't know if it's a maximum or a minimum error. We know that this is the maximum error, and the maximum error can go both ways. You can go plus or minus on the maximum error. Now, here's the part C. So far, this was the only weird part, but we accept it because this was an online exam. Let's talk about what happens when we want to use the Taylor series. Sorry, the alternating series. So using results and methods, find the best possible error for the approximation. So basically, they're saying, can you find a better approximation for this? Right, so using the results, we want to find two positive numbers, A and B, such that f of 1 lies between T8 minus A and T8 plus B. So basically what they're saying, and they gave you this in here, that you need to use the alternating series to get a better result of your approximation. Again, this was an online exam, so there was a lot of, they were trying to make it a little bit more difficult than average. I don't anticipate your test being this weird. So how can we use the alternating series? Look, your f of x is equal to e to the x minus 10 cos x. So clearly, we cannot use the alternating series here. Can we agree to this? So clearly, there is no alternating series. This one is the alternating series. This one is just the summation of x to the n over n factorial from n equals 0 to infinity. So for this one, we're going to use the Taylor error. For this one, we're going to use the alternating series error. So we're going to do a better result than what we did before. We're going to better approximate this by giving you a Taylor error for this, but an alternating error for this. Look, so if you take, it was called A of x, right? So this is the Taylor polynomial of degree 8 of e to the x. So this is Taylor n is equal to 8 for e to the x. Right, we found it to be 1 plus x plus x to the 2 over 2 plus dot dot dot. The last term was x to the 8 over 8 factorial. So what would be E8 in this case? E8 of 1. What would be the Taylor error if I'm focusing my energy only on e to the x? What would be the Taylor error if I'm doing the Taylor polynomial of degree 8 only on e to the x? That would be the ninth derivative of e to the x. So the ninth derivative of e to the x divided by 9 factorial times d to the 9. We agreed that d is equal to 1, and we know that this is the maximum value of e to the x, all divided by 9 factorial 1 to the 9, right? The ninth derivative of e to the x is e to the x. And if we're looking on the interval minus 1 to 1, what gives me the maximum value on this interval? The maximum value on this interval is at x equals to 1, right? It's e to the x, and you're looking at it from minus 1 to 1. So the maximum value happens when x is equal to 1. So this is e over 9 factorial. So e to the power 1 is between a1 minus e over 9 factorial and a1 plus e over 9 factorial. Let me say this one more time slowly. This is the Taylor error, right? So this is the Taylor error bound for e to the x if approximated by a of x at x is equal to 1. Now we're going to do an alternating series error for 10 cos x. So if I take minus 10 cos x, right? So this would be the sum minus 10 times the summation from n equals 0 to infinity of minus 1 to the n, x to the 2n over 2n factorial. Right, so this would be the summation from n equals 0 to infinity minus 1 to the n, 10 times x to the 2n over 2n factorial. Right, so if I want to use, if I want to stop at degree 8, right, so that means I'm going to say for n is equal to 0, this is going to be minus 10. For n is equal to 1, that's going to be 10x squared over 2. For n is equal to 3, that's minus 10x to the 6 over 6 factorial. For n is equal to 4, this is n equals 0, 1, 2. This is, hold on, I made a mistake. So n is equal to 0, n is equal to 1, n is equal to 2. N is equal to 3. N is equal to 4. Right? So that means, what's the first term left out? The first term left out is plus 10x to the 10 over 10 factorial. Right? So the first term left out is 10x to the 10, 10 factorial. And if we're using it at, to approximate t equals to 1, let me think about it for a second. How do we formulate it? That means 10 cosine of 1 is between, right? So the error is 10 over 10 factorial, right? The first term we leave out when x is equal to 1. Remember, x is equal to 1. We're finding the error when x is equal to 1. The first term we leave out is 10 over 10 factorial, which is basically 1 over 9 factorial. So the error is 1 over 9 factorial. We're doing plus to get that. So this is an underestimate. So that means this is between C1 oh shoot, why did I say minus 10? Somebody should have stopped me. Sorry, this is plus 10. There's no minus here. So plus 10, plus 10, plus, minus, plus, minus, plus, minus. Sorry, there was no minus there. So this, the next term is a minus, so this is an overestimate. So that means 10 cosine of 1 is between C1 and C1 minus 1 over 9 factorial. Right? Because C1 is an overestimate, it's bigger than. So if you add both, so here you take this and you combine it with this. And now you have that e to the 1 plus 10 cosine of 1 is between C1 plus A1 is T8 of 1 plus E over 9 factorial. And this one is T8 of 1 minus 1 over 9 factorial minus E over 9 factorial. So A would be just 1 plus E over 9 factorial, and B would be E over 9 factorial. And why is alternating series better? Because alternating series only puts a constant on one end, because we know it's an overestimate. So we know that the constant only goes on one end. We don't have to do like we did in Taylor, plus and minus the error. Again, this is the worst case scenario in my opinion. Like this was a very difficult problem, especially part C. Part A and B maybe were simple, but part C is a little bit weird. I don't think a lot of people got it. It was an online exam. I don't know what happened during that year. But this illustrates again the difference between the Taylor error, where you do minus the error and plus the error, and alternating series where you know that it's an overestimate, so you put the error only on one side. So if this was an underestimate, we would have had plus 1 over 9 factorial and then took away the minus 1 over 9 factorial from it. Okay. Before we move away from this, let's just look at like a normal test, like not like an online test. What happened on April 2019? So before COVID hit, let's see. Look at this. So let's look at the type of questions that were not like an online exam where they were trying to, not give them the same questions they did in class and whatnot. So let's look at 2019. Again, I'm doing this so you don't sort of freak out and think, oh my God, this is going to be the worst test and blah, blah, blah. So let's see. I'm copying these both here. Okay, so calculate the first 5 terms of the Maclaurin series. So the function is 1 plus x to the minus half. So the first derivative is minus a half 1 plus x to the minus 3 halves. Then 3 over 4, 1 plus x to the minus 5 halves. Then minus 15 over 8, 1 plus x to the minus 7 halves. Then 7 times 15, that's 105 over 16, 1 plus x to the minus 9 halves. And at 0, that's 1, minus a half, 3/4, minus 15 over 8, and 105 over 16. So you want to find T4 at x. It's f of 0 plus f prime at 0 x plus f double prime at 0 over 2 factorial x squared plus f triple prime at 0 over 3 factorial x cubed plus f to the order 4 at 0 x to the 4 over 4 factorial. So was that difficult in any way? It's just a bunch of derivatives that we are just plugging into T4. Okay, so let's see. I'm going to copy this because we're going to need it. So for the Maclaurin series in Q7, for x equal to 0, the Maclaurin series that we find in question 7 is alternating. So they're telling us that it is alternating. Use the alternating series error to find an upper bound on the error. They're telling us it's an upper bound because it's plus, right? So we're doing T3. This is T3. So when we're using the alternating series error, we're adding the next term. So this is an underestimate. So it's an upper bound on the error anyway. If the degree 3 Taylor polynomial is used to estimate f of 0.1, which is 1.1 to the minus half. So we're saying T3 of x is equal to 1 minus 1/2 x plus 3 over 8 x squared minus 15 over, divide this by 3, that's 5 over 16 x cubed. Right, so if we're doing T3 of 1.1, that would be 1 minus 1/2 times 1.1 plus 3 over 8 times 1.1 squared minus 5 over 16, 1.1 cubed. What's the first term left out? I don't know, I'm going to calculate this. So 105 divided by 16 divided by 24, that's 25 over 128. 1.1 cubed. So this is the first term left out. So that means the error is less than or equal to just B3. So 25, actually it's 35. I copied it wrong. So 35 over 128 times 1.1 cubed. But the error is less than the first term we leave out. Now, they're saying check your work with an explicit calculation. So find what f of 0.1 is, find T3 of x, sine f of 0.1 minus T.3x, and then use the upper bound on the error given by Taylor's inequality. Wow. So that's, well, use the alternating series error to find an upper bound on the error, blah, 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 to estimate this. Now, the answer is this. Now, let's say you want to use the Taylor bound error. So that would be E3, which is the maximum value of f to the order 4 at x, divided by 4 factorial d to the power 4. I'm so sorry. I made a mistake here. It's t of 0.1, right? F of 0.1 is approximately equal to t of 0.1. So it's 0.1. So 0.1 cubed and then 0.1. I only caught this when we were looking at the Taylor polynomial. So let's see where this is the Taylor centered at 0. We're evaluating the error at 0.1, so that's d equals to 0.1. The fourth derivative is given to us by this. This is f4 of x, f to the 4 of x. We're looking for it on the interval minus 0.1 to 0.1. We can close it if you want. So how do we get the maximum value of this? How do we get the maximum value of this? Because this is in the denominator, we want x to be as small as possible. So the maximum is when x is equal to minus 0.1. So the maximum error bound at 0.1 is 105 over 16, 0.9 to the minus 9 over 2 times 0.1 to the 4, all divided by 4 factorial. And that's the error bound according to Taylor. We can calculate it if you want, but I don't think that matters. So 0.9 to the power minus 9 over 2 times 0.1 to the power 4 divided by 24, and the error is 0.0000439. If you want to calculate this is 35 divided by 128 times 0.1 to the power 3, and that is 0.000273. Of course, those are two separate errors. And that's how we calculate the alternating series error, and that's how we calculate the Taylor error. We discussed how we find the Taylor series. We discussed how we find the Taylor polynomial. We basically did everything in 3-4 times examples of each. And that's series, you guys, for your test. So tomorrow, we are going to do multiple integrals, which is also not a super easy topic, and it takes a lot of practice. So the theme of the day is please, please, please practice, 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 practice. It's not a topic that you just learn like this. It's not like tangent planes, like you know what to do in tangent planes, you calculate it and you go on, right? It's a topic that even if you know what to do, it just takes some practice to get used to. Any questions, any comments, anything at all before we call it a night? Right, well, thank you for coming. Thank you very, very much for being here. I hope this was helpful, and I shall see you tomorrow for some multiple integration. Head office, thank you very much and good night. See you tomorrow.